too late last night, so I apologize if I'm a little groggy for the first part of this lecture. But we are on lecture 4 of this sort of colloquium on the quantum phase of the wave function. And this is going to mark kind of, I would say, like the end of the first arc of this class, where the idea of this was to sort of approach the quantum phase from this sort of like Madelung picture and gain intuition from it. So I'm going to call this, if you, I should post the notes. I'm going to call this lecture a little different than what I actually call the notes, which I guess is the theme. I thought it was kind of cheeky, so let's call this new physics, quote unquote. And I say that because so far, what have we done in this course? I drew this diagram that I'll redraw again in today's lecture. So in this course, for like lecture 2 and part of lecture 3, we were talking about basically matter. So this is like the wave function, wave, and just like something like this. So this is sort of a thing, and the equations of motion of matter in quantum mechanics, not in classical mechanics, were governed by the Schrödinger equation, or in lecture 2, we should have shown that this was almost equivalent to the Madelung equations. Then in lecture 3, we introduced this new object, which was the gauge fields. So we have electricity and magnetism, which sort of includes the gauge field, phi and A, and also the electric and magnetic fields, which were the gauge invariant manifestations of those things. This thing we showed, and this sort of existed independent of this, but we know that E and M is a thing that exists, and we knew that quantum mechanics was something that exists. So in order to couple these, we had sort of a thread which tied both of these together, and that was by imposing local phase symmetry on quantum mechanics. You essentially get electromagnetism, and with the caveat that you need one extra thing in order to complete this. And there were sort of mechanisms by which these two things were coupled that are sort of less abstract than local phase symmetry. I think the least abstract was, if you want to measure these fields, you need to somehow understand how they affect matter. So we derived the Lorentz force law. I'll just write it, which was something like this, right? Really, we took a classical limit of an equation we got, and we find that we get the Lorentz force law. So this is how these affect matter. I also showed that from the definitions of these, right, where D was the curl of A, and then E is like the gradient plus the time derivative, that you can get two of Maxwell's equations, which I'll call the Bianchi identities. So those were that the divergence of the B field is 0, and the curl of the E field is minus partial B partial C. So this sort of tells you how, just like how the Schrödinger equation sort of tells you how like matter like evolves, this tells you, independent of matter essentially, how the fields evolve. Now this isn't complete, right? Maxwell had 4 equations, and we, at the end of the last lecture, I just didn't quite have enough time to derive them, and also because it's more advanced, but I did go over them briefly. There was a way to show how matter influences electricity and magnetism, and that is just the other 2 Maxwell equations, which you can get from writing down a Lagrangian, and the extra missing piece that I mentioned earlier was imposing Lorentz symmetry, and that's how you would get that. So these would be the remaining 2 Maxwell equations, which notice each have sources. So the way that I wrote this was like, this is Gauss's law. Here, rho is like the probability density, so this thing is like that. And similarly, you have the Ampere-Maxwell law, which in reality, right, it's mu naught times J, I guess QJ, because this is technically the probability current, and multiplied by charge gives you the like actual current density, plus epsilon naught times partial E partial T. This one could technically also fit in sort of this category because this tells you how the B field evolves according to the E field. So maybe I should put that in this arrow. Unfortunately, this thing kind of muddies this nice picture that I have. But regardless, you did, because this one has a source charge in it, or a source current in it, we had to use a Lagrangian method. Anyways, the details of this aren't super important, but I did want to draw this because notice that nothing here is new in the sense that you had already seen everything before. We already derived the Madelung equations. You were familiar with quantum mechanics in 1D, at least from 115A, and from your other classes, 23, 24, if you took CCS, maybe 34, or even high school, you're probably familiar at least with the ideas of E&M, and you've probably heard of the Maxwell equations. So we haven't actually done anything new, as in developed a new theory. We haven't gotten new physics yet. The only thing that's new that we've done is this thing here. So we've imposed local phase symmetry, and that causes the connection between these two things. So in order to see anything that is new, that isn't something that we've already seen before, we're going to have to find some effect, some phenomenon, which combines both quantum mechanics and electricity and magnetism, and see if there's something new there. And that's sort of the goal of this lecture. We'll cover two examples of how intertwining these things gives you results that you wouldn't have with either of the two original theories. Let me quickly post the lecture notes before. They should be up now. Yeah. Okay. I guess I have this kind of awkward space to use. Before we do that, I need to do two prerequisites, two preliminaries. Because in our discussions previously, we didn't quite cover everything that I think we should in order to fully understand this in a meaningful way. So I'm just going to cover two things that might seem a little bit unrelated to this, but will definitely tie in once we get to the end of the lecture. The first thing that I want to cover is the quantum potential, which is this thing here, which I'll say is explicitly a function of position and time, which is minus h bar squared over 2m times in 3D, right, the Laplacian of the dome of the wave function divided by the dome of the wave function, right? So this thing, remember, this thing has importance in the Madelung equations, which I will also write down now, because I think probably it's good to see. So remember, the Madelung equations were this, divergence of rho v equals 0, and minus h bar partial theta partial t, where this thing is epsilon, is equal to 1/2 mv squared plus q, where q sort of pops in here. This is, these equations are, before we do any local phase symmetry, these are just going back to lecture 2 before we tried to talk about E&M, just sort of vanilla quantum mechanics transformed into the Madelung form. So, in these equations, so far all that we've done pretty much is to show that, well, these sort of look like fluid equations by taking the limit as h bar goes to 0, which is the classical limit. And that just means that q goes to 0. Or in last lecture, when we did do E&M, we also considered the h bar goes to 0 limit to get the Lorentz force law in a way that was the most familiar. So far we pretty much haven't talked about q at all, even though this is arguably the most important piece of the puzzle because it's the thing that actually just differentiates classical and quantum mechanics in this formalism. If you did try the second homework, you would have seen some of the effects of this. If you didn't, then don't worry about it, but I did put those on there because I felt like there wasn't enough time to really discuss Q, but here I want to do it a little bit. And the role of Q is, if you remember back to the Euler equation, it acts like a potential, right? It looks like potential. It's called the quantum potential. And so it acts like an internal pressure of the quantum fluid. It's a weird type of pressure because it depends on this weird thing. It depends on the Laplacian of the norm divided by the norm. And really, if we wanted to express it in terms of Madelung variables, we should write that as like the square root of rho, right? Because that's that. And remember this is this. But in order to illustrate what exactly this is and what it does, I think that the most illustrative example that we can talk about is interference. So let me, So interference is entirely caused by the Madelung equations. Caused by the quantum potential. So in the Schrodinger equation, in the Schrodinger picture, you guys are pretty familiar with how interference works. You have, say that you have two solutions to the Schrodinger equation, psi1 and psi2. If they're both solutions, then you can just add them, and you can add any combination of them that you want, up to normalization, right? And this new psi will also be a solution to the Schrodinger equation. This is just a statement that the Schrodinger equation is a linear differential equation. If the thing that we measured was just the wave function, then we wouldn't have any interference, because literally it would just be like you can superpose things and it just looks as if, it's like imagine putting two sine waves together. Like you just superpose them and they just look like they're bigger sine waves. You wouldn't see anything that sort of looks like a sort of wavy thing beyond what the original waviness of these two was. And that's because of this linear property. So why do we have interference? It's because the thing that we measure isn't psi, it's the norm of psi, right? So if I write out the magnitude squared, which is really what we measure of this, we get psi1 squared plus psi2 squared plus, I think it should be 2 norm psi1, norm psi2, times the cosine of their phase difference, where theta 2 and theta 1 are like the phase fields attached to each of these, right? And this could be swapped because cosine is even. So the point is that now it's specifically this thing, which only happens because you take the square of the wave function, which is the sort of interference term. This is the thing which causes the interference. Explicitly it's like this cosine, right? So all of the interference comes from the difference in the phase of wave functions. That's something that you learned in 115A. You're familiar with it. It's like if you have a relative phase on these, then, which this is, then you can have some sort of beating interference pattern that comes from when you take the square. And note that these things also vary in space and time. These are each functions of space and time, so this is not like a trivial thing to write down. It's trivial to write down in this form, but it could be very, very complicated because theta 2 and theta 1 could vary however you want, pretty much. This makes sense in the Schrodinger equation. I think it's a very easy thing to see. I honestly think that it's a little bit more physically motivated when you move to the Madelung picture. Although it is a little bit more difficult to get started with. In the Madelung picture, so this is Schrodinger equation. In the Madelung picture, let's see Madelung down here. You don't have a linear equation, right? If I look at these, what is nonlinear about this? This thing is linear pretty much, right? There's these multiplications. I guess when I say linear, I mean in terms of rho and v. And the most nonlinear thing about this equation is in fact the quantum potential. Because again, I can write this as square root rho over square root rho like that. This is like a highly, highly nonlinear thing. And so this thing means that if you have rho 1, like rho v is equal to rho 1 v1, where I'm sort of adding these together component-wise, plus rho 2 v2, even if these two are both solutions, this thing is not necessarily going to be a solution. Probably won't, almost certainly will not be a solution to the Madelung equation. So we don't have linearity anymore. And that should make sense because rho is this, and this thing clearly does not add linearly in whatever framework you work in. But then it's a little bit more confusing as to like how would I actually calculate what the interference is. And there's more sophisticated ways to do this than the one that I'm going to show, but I just want to show one example that sort of illustrates what the quantum potential actually does. I guess I'll do that. Yeah, I'll draw it up here and we'll do a little bit of derivation here. So imagine that you have, yeah, we'll do it. Imagine that you have two wave packets, which I'm going to draw the wave functions for. So this is the magnitude of the wave function. And the two wave packets are, say, they look exactly the same at the particular time that we're going to look at them. They look like, that's a little poor. They look just like freestanding Gaussians, and this is a free particle, so we'll ignore the potential. That isn't quantum. Okay, suppose that these are perfectly overlapping. I'm just drawing them slightly different so you can see the difference. And this is just some coordinate. I think I use y for some reason in the notes, so we'll use that, but that can be x. It's just some spatial coordinate. And say that the equations of motion, or the wave functions at this particular instance in time for these wave packets are almost identical. So let's call this psi 2 is e to the minus alpha y squared, e to the minus I k at ky. And the wave function that's red, which by the way, can you see the red? Is that, tell me if this is seeable, is that? I'm gonna say that's okay. Okay, this is equal to e to the minus alpha y squared, e to the I k y. So the only difference between these two things is the sign on this sort of like wave, that's the sign on this like k that's attached to them. So they're just Gaussians that are propagating in opposite directions that happen to coincide at this particular snapshot that we're looking at them. In the Schrodinger equation, right, it's very obvious, or we can immediately sort of calculate what the interference pattern of these is going to be, right? We can draw this sort of superposition of wave functions, but because of the difference in phase, there's going to be this very not smooth, or I guess it'll be a very wavy pattern that we'll actually see when we take the norm squared. So if I were to just immediately write down what the wave function is for these, I can just write it down pretty simply because this is the complex conjugate of this. So it's just 2 e to the minus alpha y squared times the cosine of ky. Does that, I maybe made a little bit of a jump there, but did people follow why and how that worked? Okay, cool. And then if I take the norm of this, right, it's just the norm of the cosine. And then I square it. This thing becomes 4. This becomes minus 2 alpha y squared. And this becomes cosine squared, or I can just get rid of the norm because it's real and call it cosine squared of ky. So immediately we see the waviness in the magnitude, but it sort of just like appeared because of this. And we can use the quantum potential to inform how this sort of happened, like what exactly caused this to happen, because it was Q. So, okay, if you calculate, I'm not going to make you work through this, but if you calculate the Laplacian of this thing, so not the square, but just the norm, so take the square root of that, you'll find that it looks something like e to the minus alpha y squared times cosine of ky times 4 alpha squared y squared minus 2 alpha minus k squared minus k sine ky. Okay. If you divide this out by the norm, so maybe I shouldn't have squared this, but if you divide this out by the norm, a lot of things will cancel. And you can just show that, therefore, q is just, remember, dividing out by the norm of this thing. So, dividing by the square root of that thing. So you find that q in this situation is a function of y, because we're not going to, it doesn't have any time dependence in this case, is minus h bar squared root 2m times the norm of 4 alpha squared y squared minus 2 alpha minus k squared plus 4 alpha y ky, we'll say, tan of ky, tangent of ky. Okay. And why did I write this out? It's because if you sort of analyze this thing, notice that where are the peaks in this? They're going to be at integer multiples of n pi over k, right? Just because of cosine. And where are the troughs of this? Like the places where this goes to 0. It's also at integer multiples of n pi over k because that's where the sine of ky goes to 0. But notice that in between, where the troughs of this are, which are odd integer multiples of n pi over 2, and I'll draw this so it makes more sense, but I'm just saying it out loud. The odd integer multiples of n pi over 2, this goes to 0, but this is a 1 over cosine, so this is going to diverge. So exactly at the troughs of the quantum, at the peaks of this, the quantum potential is the weakest, and at the troughs where the probability goes to 0, the quantum potential diverges. So let me draw that. Maybe say down here, so we can say.
This is similar to what you'd expect from the Schrödinger.
It's exactly the same thing. This is literally just providing like a slightly more, like, I want to say a slightly more intuitive way of understanding it, because essentially it's like the quantum potential is acting as a pressure which pushes the fluid away from the high energy penalty points. So let me draw it so maybe this makes a bit more sense. So we have, now we have the norm squared of psi, and then we'll also put, or you know what, let me put the norm squared of psi in purple, and now I'll put the quantum potential in yellow. So if I draw the norm squared of psi, it should just look like a Gaussian envelope, right? It's sort of, but that is sort of oscillating, so something like this. Maybe not. Something like that. So that's what the wave function magnitude looks like. But the quantum potential, if you draw it and you actually like draw what this looks like, I'm just gonna do this one because this makes it basically, it gives you like a parabola that, the parabola means that overall as you increase y, the quantum potential increases parabolically, which is why these peaks get smaller. But if we just plot this part, so I'll say, we're really plotting this part, it's a little bit clearer. The quantum potential looks something like this. Let's see, it like diverges at each of these troughs. It's something like this, and then something like this. It actually has like a kink at this, and sort of it would look narrower. Yeah, let me not clutter this too much, but you can sort of see that exactly at the places where the wave function is maximized, the quantum potential is minimized. So even though this is a free particle system, the quantum potential acts like an energy penalty. It literally says there's an infinite energy penalty for any wave function to be there. So it literally has to be 0 because the potential is infinite there. Whereas at minima, you have maxima in the wave function. And again, these minima are smaller because there's actually this parabolic term that I'm not drawing. So even though this, we already got, like in order to get this, we already derived this thing. So you could have gotten the interference pattern of the wave function without citing the quantum potential. But in the Madelung equations, this sort of gives you a reason that maybe feels more intuitive as to why there is interference in the first place. It's because the quantum potential sort of pushes the fluid into these wavy patterns. And this will be important pretty soon. Okay, so that's the first topic, or like preliminary, that I wanted to cover today, the role of the quantum potential. This is sort of like, so let me just say, we can see the onset of quantum effects when interference becomes more apparent. That's literally like saying when Q is more important, we should see more interference. So it's like a heuristic. We can kind of use that to see, is this a very quantum effect or not? Or in a quantum regime or not? Let me pause here before moving on to the second thing. Any inquiries, questions about this so far?
Yeah. Could we go back like a couple steps to when you just took the norm squared of psi?
Yeah.
What happened? I thought I understood, but what happened to the first two terms in psi squared? Do they just cancel?
Sorry, the first two terms?
Yeah, like you just norm psi 1 squared plus norm psi 2 squared.
Oh, yeah. Well, I just wrote, like, psi ends up looking, I mean, you can write it like that, but psi just looks like this, right? Because when you add these, this is, okay, maybe I can,
wait.
Let me be
I feel really silly right now.
No, it's cool. Let me just like do this so that like if anybody else is confused, it's literally just psi 1 plus psi 2 is equal to e to the minus alpha y squared times e to the I k y plus e to the minus I k y, right?
Yeah.
So then this is just 2 alpha.
Oh, okay.
Yeah.
I see what you did. Yeah, okay. You didn't use that formula, right?
No. I chose an easier example here because I think that this gives the same illustration. But yeah, if I wanted to, I could do that.
Okay.
Yeah. I'm gonna just square that. Okay, cool. Anything else? All right. So the second thing, which is actually probably a little bit more relevant to what we're doing, but will maybe seem a little bit newer, is the concept of circulation. So this is touching back on something that I mentioned in week 2, which was like this issue of when we derived the Madelung equations, and this is illustrated by the fact that you had this 1 over square root rho or 1 over norm psi in Q. When we derived this equation, we took the imaginary part of the Schrodinger equation, which we had separated out, and we divided out by the norm of the problem is that when you do that, you are assuming, right, that there isn't any place where the wave function like goes to 0, where the norm goes to 0. But clearly, I mean, I'm just giving you an example where plenty of places the norm literally goes to 0, and so that's like no longer a valid thing to do. Right? So clearly we have, in order to say that this is equivalent to the Schrodinger equation, we actually have to make a clarification about what happens at those points where the norm goes to 0. And immediately we could say, like, well, what does happen? So if the norm goes to 0, then because the theta field is defined as like, it is the complex phase angle of the wave function, well, at 0, then theta is undefined. Right, so that's a huge issue. So this phase field, which this entire thing is based on the dynamics of, there's no wave function in here besides Q. The phase field becomes undefined, so that equation ceases to like make sense at those points. And this is mostly okay if we say that, okay, let's just, let's say partition this into regimes where we have finite wave function magnitude. Yeah, but like what happens if I sort of cross over a node in the wave function, let's say. A node, I'll say, when I say, I'm going to use the terminology node in the wave function, and that literally just means like a place where the wave function goes to 0, kind of like at a point. So we want to consider, in order to sort of complete this theory and make it equivalent to the Schrodinger equation, how do we deal with this? I guess I should say not goes to 0, if this is equal to 0. To illustrate that, I'm going to choose probably the simplest possible example that you can. Again, you can do this more generally, but I think that this is good enough. So we're going to consider a two-dimensional system which has coordinates x and y, right? And we'll say that this is just equal to, the wave function is equal to x plus I y quantity to the power n with n an integer. Okay. Maybe so that you know exactly what we're doing, I'm literally saying we have a coordinate system with, in 2D, with x and y coordinates, and we're considering the wave function as living in this space. And I'm just saying that it's this, you know, I haven't drawn the normalization because the normalization is pretty unimportant for this.
1 second, I don't understand. If psi equals 0, then theta is undefined. Maybe I'm not seeing that.
So it's because if the norm, so psi, let me maybe write it over here.
Psi equals mag psi times e to the I.
Yes.
Right?
Yes. So if the norm of the wave function is 0, then psi, like the whole thing is 0. And so it doesn't matter what theta is, right? Like,
Okay, in that sense. Okay.
in that sense, it's undefined.
Sure.
Yeah.
Okay.
Like, yeah, in the sense that like you don't need to specify theta.
Yes. Okay.
You don't. It's undefined. Yeah, or you could. Yeah. Okay. So this constructs a situation where this is where we have exactly one point where this happens. And it makes a little bit more sense, I think, to think about this in terms of polar coordinates. So I can write this as r to the n, where r is the polar coordinate in this 2D plane. Maybe let me draw. If I have some ray here, this would be r. This is, say, a vector r which has magnitude r and has angle phi from the x-axis. So it would be r to the n times e to the I n phi. Okay. As you can see, when r goes to 0, at the origin we have a node in the wave function. And from this we can immediately calculate the norm squared, right? So the norm squared is just r to the 2n. So this is rho. So we have rho equals r to the 2n, and v is equal to, let's say, yeah, let me just ignore the constants outside for a second. So I'm just going to work with the gradient of theta for simplicity in a second. So just the gradient, ignoring the constants, is equal to the gradient of n times phi, which, if you work this out in cylindrical or polar coordinates, this is equal to n phi hat divided by the radius r. Are people cool with that? So I'll box these. These are kind of important. Good. Okay. So now let's say that we wanted to find like the difference in phase at two different points.
Can I make one comment? So, I mean, you specialize to 2 dimensions,
Yeah.
and your wave function is complex. And so if you ask, you know, what are the typical zeros going to look like? Are they going to be lines or points? They will be points.
Right, sure.
Because you have to tune both the real and the imaginary parts to 0.
Okay, maybe that's a fair thing to say.
Like in 3 dimensions, there would be lines if you have a complex wave function.
Right, you could have, right, so I guess maybe I can, I'll elaborate on this a little bit more. I don't want to get too much into the details, but like this, I've chosen this 2-dimensional system because you have nodes in the wave function that are points. So it's just like a point where the wave function goes to 0. You can imagine, like, basically I can turn this into a 3D system very easily by just saying it's the same 2D system and I give it, you know, like symmetry along the z-axis. And then that would sort of stretch this point into a line where the wave function is 0. Of course, in 3 dimensions, you also could have a situation where the wave function is 0, but it's like at a point. And for reasons that are kind of maybe will be understood a little bit better in like half an hour, those are maybe less important for what we're considering here. We're kind of, yeah, we'll see. We'll see in this situation, this is a node that's going to cause something to happen. And I've chosen this example very specifically to illustrate that in a way that's very simple and like easy to understand. Sorry, is that?
Yeah, if the wave function was real in 2 dimensions, then you have nodal lines in 2 dimensions. Could you just have tuned the
Sure, okay, yeah.
real part?
Yeah, you could also have, you could have whatever you want, right? You could, I mean, like, yeah, it basically just be this. And if you sort of stretch this out, you could have nodal lines. But I'm not, like, you could have a lot of situations. I guess this one I think is this is primarily illustrative.
But it's kind of generic. If you have a complex wave function and you're living in 2 dimensions, you have to tune both the real and the imaginary parts of the wave function to 0, so you have to tune 2 parameters in the y and the x.
Yeah, okay. That's,
So it's kind of generic.
Okay, sure. Yeah, if you have 2, sure, that makes, I didn't actually think about that before, but yeah, that makes sense. So it's generic, and I guess also, we'll say you can have nodal lines if it's real, where you kind of have this like, I don't know, you sort of have a trough where it goes to 0. But there, right, if that's a real wave function, then also we're mostly interested in like the phase dynamics of this, right? So if the wave function is real, then the phase dynamics are pretty much just going to be trivial, right? Because the phase is real for everything. But yeah, like, okay, so yeah, in 2 dimensions, generically we should have singularities or nodes that look like that. And this is probably the simplest characteristic example of this, where it's literally, all I'm saying is that it goes, like, you could write this as like the complex number z, right? This is just some arbitrary complex number z. So it's just going to 0 at the origin arbitrarily to some power n. So this is like a very generic idea. I mean, it could decay to 0 faster or slower or whatever, but this is a simple one, and often it will look something like that. Okay. So if we want to calculate the difference in phase, or if we want to consider what the difference in phase is between 2 points, right, in 2D space, so I can draw them, say this is R1, and I have another point R2, so this is vector R2, meaning like R2 comma theta 2. So this is say V1, V2. Then we know the difference in these if I just write delta theta, where theta is like the difference in the phase of these. Well, that just has to be n times phi 2 minus phi 1. So, okay, that's true. Like that just seems like it has to be true. But we should also think that this is something that is true because we could also consider trying to calculate this difference in phase. And you would calculate that by considering some path from R1 to R2, say this, we'll call it C1 for, just call it C1 for simplicity for now. And if you integrated integrate over C1, where C1 runs from R1 to R2, of the gradient of the phase, dotted with this sort of infinitesimal line vector which runs along C1, then this thing has to also be equal to this. And because gradient of theta is a conservative vector field, clearly, it's going to be the case that you can just write that this is true because this is just the gradient of theta, the integral, or like the antiderivative of the gradient of theta, evaluated at each of the endpoints. So this is right where if you sort of go backwards, you just basically evaluate theta at each of the endpoints, which is n phi 2 minus n phi 1, and that just is like a confirmation of what we would expect it to be. So this is very very simple. Like I hope I don't want to overcomplicate it. That's literally all we're doing. The reason why this situation is a little bit less than trivial is because if we consider a path that, say, encircles the origin, then we have a slight difference, right? So if we want to find the difference in theta at one point between itself, you should expect that the difference in phase has to be 0, because it has the same phase, right? So, but if I calculate that, then let's say delta theta over C1, delta theta over C2 is going to be the integral over C2 of the gradient of theta, which I wrote here. This is n phi hat over r, dotted with dl. Well, dl is some combination of, you know, r and theta vectors, but because we're dotting it with n phi hat, I can just only consider the phi hat component, which will have a Jacobian of r, right? So this is just r d phi phi hat, and then if I calculate, if I do this, then you can see phi is going to range from 0 to 2 pi, and we can pull the n out. So we have n from 0 to 2 pi of d phi, which is just equal to 2 pi times the integer n. And so this isn't 0. And that is a problem, except for the fact that, right, the phase is defined modulo 2 pi. Because this is really not just, this isn't just a normal scalar field, it's a scalar field which is defined in the complex phase of the wave function. And if you add 2 pi to a phase, that doesn't, you know, it doesn't actually change what the phase is, it might change what the angle is, but those are equivalent modulo going around this circle once. So, why did this happen? Right? Normally, if I were to instead sort of calculate along some path that was more like going like this, you'd find that you don't actually have this 2 pi, it would just be 0. So it's the fact that we encircled this node in the wave function that we actually get a let's say, I don't want to say non-trivial, but like a non-zero phase difference that is still a multiple of 2 pi n, so it sort of allows the wave function to still be single valued. And all of this comes from the fact that we encircled a node. And yeah, I don't really want to completely prove why this is the case here, because I think that the nicest way to show it is using a little bit of complex analysis, and I don't think that that's quite something that I want to expect you guys to know. So I'm just going to say that this is an illustrative example of a more general principle, which is simply that we can define the circulation of around some point of the wave function as, so remember this thing is defined as m over h bar times v. So if I consider integrating the gradient of the phase along some closed path, call it over some path c, we call this a circulation, and we integrate the gradient of the phase. This thing has to be an integer multiple of 2 pi, and I'll use k here, where k is an integer, to sort of differentiate this from n. Notice that this one says that, you know, if you increase the power, the phase is gonna increase by 2 pi that number of times. I'm saying generically, for any wave function, at least in 2D that encircles a node like this, you have circulation of the phase by some integer multiple of 2 pi. Okay, and this in this picture kind of gives an interesting, it has an interesting idea behind it, and that is that the gradient of the phase without, you know, before we introduce phase symmetry, is directly related to the velocity of this probability fluid. And so that's like saying that the velocity of the probability fluid, you can actually sort of go around a node, and it acts kind of like a vortex, right? Where you can encircle it and you actually gain velocity as you move around it. So you would see like in the, if you were to sort of plot the vector field, you would actually see like the arrows sort of going around the node. And this is to say like, and this is sort of non-obvious because you would expect that you can't have any sort of circulation because you know that the curl of a gradient is 0, but when you have these nodes of the wave function, it actually allows you to do that. And you can show that like the curl of the wave function is a delta function at those points. Or sorry, the curl of the phase, curl of the velocity field is a delta function at those points. So this is a little bit, yeah.
So just like, I know we're not supposed to talk about complex analysis, but just a quick question. So this bottom formula of gamma here is general, right? For any delta theta, right?
Yes.
Okay.
This is, I mean, this, I could have just said is imposed by single valuedness of the wave function. I guess the non-trivial thing is that k can be non-zero, but.
Yeah, and if I'm understanding correctly, from like the complex analysis side of things, that's because you could expand psi as like a general psi as a Laurent series of these little ones here.
Yeah.
Okay.
And then then find the residue and then.
Yeah.
do
Okay.
those things. I would say. I think that normally, I don't know.
Can psi always have a Laurent series? Like,
I think it's fine, right?
yeah.
I mean, I don't, not necessarily, right? There's some weird things if you have, like, if you introduce a potential and say you like a step. So I guess.
Oh, I guess like the delta well or something would work, right?
Well, the delta well, if it's in 2D, right, then you have like what it's like the magnitude. So yeah, probably not. There's definitely like cases where it's a node and this integer is 0, right?
Yeah.
But like yeah, if it's a smoothly or diverging like some pole, right? Singularity, then or diverging to 0 thing, then it probably ends up working out. I think it does. I think, yeah, you can do this, and I did work this out like 2 weeks ago. I wouldn't, I would maybe, if you want to spend some time trying to work that out,
Yeah.
but it's not like, it isn't actually gonna end up being that important to what we talked about today.
Yeah.
But,
Yeah.
Okay, so those are the two kind of preliminaries that I spent an hour on, but that allow us to get through stuff without talking about combining QM and electromagnetism. I'll erase this figure here.
So as opposed to a fluid, I mean, you can have like when you flush a toilet, there's a vortex.
Right.
But
So
the circulation is not quantized, right? And that's
Yeah, okay,
this is where
sure.
the quantum mechanics
Maybe
enter.
that's also good to say. Like, yeah, I was gonna. Yeah, as opposed to a fluid, like Matthew's saying, you have circulation, and that circulation, because of this single valuedness, is imposed to be some quantized thing. So that's like a non-trivial quantum mechanical effect that maybe you wouldn't expect in a fluid. You can kind of view this. There's a way to view this if you wanna think about it a little bit more like I don't know, more in terms of that way. Is that if we want to impose this on the velocity field, right? Then I would say that this is m over h bar. So if I was to actually consider the integral of the velocity, right? If I just said mv, then if I said this was mv, this would get an h bar. And so you can think like, if h bar is really small, then it's basically like some continuous amount of circulation that you could have. for the velocity, but we're sort of in the regime now where we're thinking that h bar is, maybe if h bar is relevant, the scale of h bar, and it's not super small, then you would actually like be able to resolve that quantization. That's a way to think about it. But I didn't put MV here because we're going to use, when we introduce electromagnetism, right, it's going to become a little bit more confusing as to what exactly we're doing. But yeah, that's a good point. Thank you. Okay. So when we add electromagnetism, so adding E and M, we do one thing which matters pretty much, which is that now our velocity is really defined in terms of this minimal coupling principle. So this is h bar times the gradient of theta, so this is so far the same, then minus q times the vector potential A. Okay, so we still know, right, that the integral of this thing over some closed loop, it has to be an integer multiple of 2 pi k. This doesn't change, because if this were to change, then the wave function wouldn't be single valued. So this principle must hold. So we can consider, but we can still consider the integral of, say, I'll include the h bar now, h bar gradient theta dot dl over some closed path c. If you consider this, and maybe this encloses a node, maybe it doesn't, but arbitrarily it could, you can write this as integral of over the path of just qa plus mv. Right, and this is dot dl. And then now this thing is equal to, because I included the h bar, 2 pi k h bar. Okay. Now we know what the loop integral of the vector field, of the vector potential is, because we could say that this thing, so if we just consider this part, right, this thing is q times the line integral, let me do it here, q times the line integral of a dot dl over the path c, and then this thing we can use like Stokes' theorem, right, to write as q times the surface integral through something bounded by c of the curl of A, which is just the B field, so it's say dot dA, which is equal to q times the magnetic flux enclosed inside of that surface. Okay, so we know this thing can be written like that. So this gives us the condition that 2 pi k h bar is equal to the flux enclosed, which we know it would be something that you could maybe even measure experimentally, plus the integral of this mechanical momentum field, so like the MV field over the arc. In the case that you have, say, 0 nodes in a wave function, right? So that's, or let's say it's 0, it's a node, but like this thing ends up being 0. So we can consider that. Then you find that you have this interesting condition that the integral of mechanical momentum is equal to minus q times the flux enclosed in the loop C. So if you imagine a system in which you have, like, say for example, the simplest system, which we'll analyze again, but imagine this is some infinite solenoid, and it has some B field passing through it, which also means it has exactly some flux. And you imagine imagine just a slice through the plane of this. This is what Matthew was saying, right? So now I'm considering a 3D system, but if I consider a 2D slice through it, then I guess actually it's not even that important. But if you have a solenoid and the fluid, say, can't penetrate into the solenoid, something like that, if I were to take this flux and I was to slowly bring it from 0 up to infinity, or up to some finite number, then you would see that, or if you could image the velocity field of the quantum fluid, you would start to see it rotate. You'd start to see it sort of circulate around the solenoid. And you can think of that either in this case, or you could also think of that as the like the Faraday, what is it? Is it Faraday's law? It's the one that gives you an EMF. As like when you change the B field, you have an electric field which causes circulation. But even without doing that, you can see that we actually require this sort of thing to start happening in quantum mechanics just by knowing that this has to be true, or knowing that this has to be true. If this is non-zero, then you would have the same thing. It's just you'd have plus 2 pi k h bar, and that would be some integer multiple of that. This is sort of teetering around some ideas of, I'll say now, it's teetering around a lot of ideas that I think feel more physically motivated when you talk about like superconductors and I guess even just BDCs in general. But yeah, I'll refrain from saying that in the main lecture because I just want to sort of keep it self-contained. This is a little bit, even still, I think this is slightly muddy for me conceptually. So if I explained it in a way that was confusing, let me also take more questions right now. Okay, cool. So this is the first thing that you can maybe think of as, well, it's, maybe I'll write this plus. It's like a quantum mechanical and also electromagnetic effect. And really the thing that makes it quantum mechanical, like Dr. was saying, is that you actually have this like partial quantization, I guess, of the velocity field circulating. But it feels not as satisfying to talk about, I think, because it's like you can't actually measure this velocity field, right? This velocity field is the gradient of the phase. It's not something that is like you could just measure it. You would have to do some type of interference experiment in order to actually see that. And so we can now sort of design an experiment around this that allows us to see what's happening here. And in this case, we'll just sort of, I guess, yeah, we'll explain what that is now. So this is now the discussion of what you guys may, yeah, this is what you guys probably have heard about now from various sources as the Aharonov-Bohm effect, which, yeah, I honestly, like, I thought about a lot for this course, and I think I feel better about it than I did before, but there's still some weird stuff about it. So please do ask questions, even though there's a chance that I might not be able to provide the most satisfying answers. Okay, so we had this solenoid thing. I think we can keep that. Imagine that this could be some infinitely thin thing, right? So say it's like an infinite potential such that you have a magnetic field on the inside, and the wave function is not allowed to penetrate the solenoid. So we've applied some B field along this infinite thing. Now, what we're going to do is we're going to say, suppose that we take an experiment which has some beam of like electrons, say, for simplicity, and it somehow splits these two beams into two paths, which then recombine somewhere like this at some screen, say. Okay, so this could be like, you could imagine putting a double slit and sort of splitting them that way, however you want. We're going to split the beams. Now, this is experimentally what you would do. Maybe it would be easiest to imagine in our picture. Imagine you have a coherent wave packet, so some wave packet that you're sending here, and then you sort of split into two coherent wave packets that are going like this, where coherent in this language means that within, say within this region, or actually you could say overall space, but within this region, V is constant. So the idea is that if V is sort of the same, if the phase gradient is the same along the entirety of the wave packet, then you won't find that the wave packet spreads, because all of it is just traveling at the same speed. Right? So we can say this is the same thing and say that these have the same V. Okay. Now what we're going to do is we're going to consider the phase change from, say, like this point to this point, or say consider the phase change between these two beams. Unlike in this scenario, where this scenario was basically done at a snapshot in time, I just said, what is the difference between these two things in phase? I'm not saying that now, because this, in order for this to occur, there has to be some time for it to take place. Like these things would have to travel around the wave packet and recombine like this. So in order to find the total difference in the phase of the wave packet, of each of these wave packets, say, then what you have to do is integrate the time derivative of the phase over time. So we can say that, suppose that this you call the place where these separate is at 0 and the place that these recombine is at t. Maybe it's hard to do that super formally, but let's just ignore that for a second and just assume that you can do that. If you want to find the difference in the phase of, say, let's call this wave packet 1 and 2. So say the difference in the phase at 1 over the time t which elapsed, you would want to integrate from 0 to time t of the time derivative of the phase, right? But the time derivative of the phase, because this is existing in, remember, this is a probability fluid, so we really what I want to do is the derivative of the phase. But this thing, the time derivative in a fluid, if you remember back to our discussion of the Euler equations, is really the partial time derivative plus the convective or the material term. So it's v dot gradient theta. So we really need to integrate this thing. And then this is integrated over time. Now, in this system, it's not that difficult. So okay, I'll just say, remember, I erased the Madelung equation, but remember the Madelung equation said that the minus h bar times the time derivative of the phase was equal to 1/2, or I guess p squared, 1/2 mv squared, was this mv is now defined like this, plus v plus q. Because this is a free particle, that's 0. Right, so we're ignoring that. Q is dependent, again, poor management, but I erased this. Q is only dependent on the norm of the wave function, right? So you will find, let's say, what you would see with Q is that actually, because the wave function isn't spreading out at all, Q within the wave packet is also 0, because that just sort of means that there's like no internal pressure that's pushing it out. If you did homework 2, you would see that like for the Gaussian, that's not true because the Gaussian wants to spread out with time, but it is possible to construct things that like don't spread out. So here, effectively, Q is also 0. So we can say that this thing is minus 1/2 h bar times mv squared. So this thing is the integral from 0 to t of minus mv squared over 2 h bar, plus this I'm going to write in terms of these guys, so plus v dotted with gradient of theta is mv plus qa divided by h bar, and then, sorry, I'll get out of your way, dt. Okay, so we can recombine this, right? This is a 1/2 plus minus 1/2, 1 minus 1/2. So we can write this as the integral from, we'll say 1/h bar times the integral from 0 to t of 1/2 mv squared dt plus the integral that has this a term, so this is plus 1 over h bar. You know what, let's put the 1 over h bar on the outside. Plus the integral of qa dot v, so qa dot v dt, and this is really from 0 to t. Okay, now the last thing that we'll do is something that I may or may not have objections to, but this thing v that I wrote, that's the derivative of the, that is the derivative of the like position of these wave packets with respect to time. So let me write dx dt. And then we'll do the physicist thing where we cancel that. And this thing now is just qa dot dx, and we're considering the difference here. So we have plus the integral, from, I guess you see it, it's plus the integral of qa dot dx. So this is the delta phase, delta theta 1. If I consider the thing for delta theta 2, it's going to be exactly the same, right? Except the, so delta theta 2 would be 1 over h bar times the integral of, times the same thing, so the integral from 0 to t of 1/2 mv squared, sorry, I guess that's maybe hard to see, v squared dt, right, and then plus the same thing, but now, right, so I guess this maybe should be rewritten. This is integrated over, call this path C1, that's path C2, right? So really this is now the integral of qa dot dx, or maybe I should have stuck to dl, and this is a path over C1, because it's a spatial path now. But now this one is plus the integral over C2 of qa dotted with dx. Yeah. Okay. So if I want to find what the actual phase accumulated, let me erase this now. So if I want to find what the actual interference pattern is going to be, which remember is just simply dependent on the difference in the phase of the wave packets, sort of what we see at the end of this experiment, then we just subtract these two. So let's see, maybe I should have ignored the deltas. Yeah, let's call this just not delta. So that's just the phase accumulated. So delta theta is just theta 2 minus theta 1, say. And these terms cancel. So the first terms cancel, and all that we'll find is that C1 and C2, you know, if we have minus C2, then that's like going around and then going back. So this is just the closed loop integral of the vector potential. So this is q over h bar, pulling the h bar factor in, times the integral of the vector potential over the whole path C, where let's say C is equal to C1 union C2. And this, as we know, is just Q times the magnetic flux enclosed inside the solenoid divided by h bar. Okay, so that is the Aharonov Bohm effect. Maybe let me say what this means. So this is the simplest possible situation that you could imagine. So here what I've done is, like, this is a wave packet that I've split, but when I split it, then I have two things which have different phases, and they accumulate, suppose that they have the same phase, but they're going to accumulate different phases over time. And so you would see an interference pattern here. You could also imagine something that had different phases originally, and then here what you would see is an overall shift in sort of the interference pattern by this constant phase shift. The point that makes this a new physics effect is that, like I said already, it's something that has both quantum mechanics, which is the fact that we're working with quantum phases, so that's already there, and electromagnetism, which is indicated by the solenoid and the flux included. And the thing that makes this really weird is that the wave packets never like interacted with the solenoid. I like at the beginning of this, I said very explicitly that there is zero, like let's say the solenoid is like an infinite potential barrier. Like you don't have wave function in there. And you know, you can say, well, what happens if you accumulate a phase because you have a node or like a zero of the wave function there? Well, that would just be a factor of 2 pi out here if you had that, so it's not important. But even though this did not interact with the B field directly whatsoever, you got a phase shift. And so it's kind of like, well, what exactly caused the shift in the first place? Yeah. Has anybody seen, like, there's probably like the Veritasium video that was posted, or like in 115B you talk about this. I don't know, but before I sort of talk about a couple of the possible explanations for this, or the let's say, philosophical explanations for this, does anybody have any ideas like what could be causing? Like what exactly is the thing which is driving this effect?
I was gonna guess that it's a geometric phase, like what you were talking about, or I could be completely wrong.
No, that's a good idea. We can understand it in terms of that. We'll do that next lecture.
Okay.
But that's a good way to think about it.
But
I don't know how much you know about geometric phases in this context, but in this context, what is the parameter that is varying?
like, I always think about it like whatever Hamiltonian I have for that state. I can also think about moving like I could change the parameters of the Hamiltonian and treat that as the particle moving.
Right. You can. So yes, you can think of it like.
And so that's my parameter space, right? It's like where I put the solenoid, for example.
Yes.
I could be completely wrong, but
No,
that's my
we
guess.
will
Yeah.
literally talk about this in that context here. I think that's fine to think about. That you can understand it that way, but I also think that it's an equally, like I'm just responding.
Yeah,
I think
yeah.
you literally can. This is like Barry's paper, but but you can also, it's arguably more natural to think about it as just like the wave packets moving. Like it feels almost unnatural, like, you know, oh, you're changing the Hamiltonian, so you have this accumulated geometric phase in parameter space.
Yeah. I mean,
You should also be able to think about it in that way.
in terms of like the fluid picture of this, I think that you could also think about one's going against the flow and one's going with it, right? Like
Yes,
of
you
the
can too.
field,
Yeah. Okay.
right?
Well, let me get to that in a second.
Yeah.
I don't know. Or did you have anything?
I mean, just the A field, we can represent it, the B as the curl of some vector field A,
Right.
and it has some sidedness to it. You know, it's curling in some direction. So, when the packet goes one direction, it goes with the A field. You can think about it maybe that way, and the other packet goes against it.
Right. Yeah. So honestly, I think that's definitely the easiest way to think about it. Where it's like literally, you're right. A literally contributes to the velocity field, like the way that I've written. So it's like A is literally just adding to the velocity, and it's like, or maybe literally is the wrong word. It's conceptually adding to the velocity, and so it's just going with the flow versus not going with the flow. I think that is a fair thing to assume. The big thing that I think that definitely like throws a bit of a wrench into that interpretation is that A is not a gauge invariant quantity. Now, of course, this thing is a gauge invariant quantity, and you can show because it's dependent on the curl, right? That flux is gauge independent. But it does mean that it's kind of a little bit confusing because it seems like you can sort of somehow change this, and the only thing that matters is the overall phase differences. So let me write down the two possibilities for things that are causing this. Either B field, you could say what you said, but the one that I actually thought of first is that the B field acts non-locally. So that would be like, it's actually the flux or the B field causing the phase shift. but it's doing it somehow non-locally because of course it can't actually like touch the wave function. So that feels wrong, or that feels weird because we kind of like locality. Or two, it is, like you said, it's the vector potential. That causes the shift. So, yes, both of these work. So that, yeah, I guess the clear issue with both of these ideas is that this is non-local. We don't like that. And the problem is that here, A is gauge dependent. So what you can do, right, and the thing is that, interestingly, because the B field is 0 outside of the solenoid, right, the curl of A is actually 0 outside the solenoid. That just simply has to be true because otherwise you would have non-zero B field. And you can imagine, right, what you can do because A is, let's say curl of A is 0, means that you can write A as the gradient of some scalar function. Let's call it just f, right? It seems like that. The problem is that, of course, the loop integral of a scalar, of a gradient, is going to be 0. So if you try to do this by basically doing a, let's see, in a gauge, when you try to do that, no matter how hard you try to do it, what you'll see is that at some point, some ray basically emanating from the solenoid, say that this happens at 0, you'll find that A is going to be singular along that ray. So it'll diverge at that ray. And what that means is that in this gauge, all of the phase difference, it didn't accumulate like a fluid flowing, so sort of going the velocity field. It's like the moment that, say, this wave, in this gauge, where I've drawn the purple line, the moment that this wave packet crossed this thing, it accumulated all of the phase difference. And over the rest of the path, nothing else happened.
So
But
this purple line is where F jumps? Is that?
Yeah,
Yeah.
this is where F jumps.
Okay,
It goes
yeah,
to
just
some,
to clarify.
right?
Okay.
But the problem is this is, and this is arbitrary. You could choose this to be wherever. I mean, I could have chosen the purple line, the place where the wave function, or the F diverges to be there. Right? That's literally a choice of gauge. So it's like, it works with the math because the actual thing that you see is an interference pattern that would be on some grading here. But you can kind of just choose it to happen however you want, and it means that you don't, like, you can't say anything about, I guess let's say, because in a gauge, because we know that this has to be a gauge independent description, or if we must stick to a gauge independent description, then that requires that all gauge dependent descriptions, or all descriptions in all gauges, are equivalent. And if all descriptions in all gauges are equivalent, then this, where all of the phases accumulated at one point, must be the case, right? It must be that, like, or let's say, like, the only thing you can really say is simply that you see a phase difference, but you don't know how that phase accumulated whatsoever. And yeah, there's arguments you can make about the geometry of the system, and saying that, well, it actually doesn't make sense to compare like the phase here versus here. It only makes sense to compare them at the same point, because you would need to say, let's say the words, you would need to like parallel transport the phase in order to do that. But it still is like, well, you don't know how the phase was accumulated, and so I don't quite like this description. There was a paper that was published by this guy in China named Shen Gao, who he was like, we need to drop gauge invariance and say that the Lorentz gauge is actually the correct gauge, which just seems crazy to me. But like this was a paper that was published in 2025 in like a legit philosophy journal. So or like philosophy of physics journal. So apparently this is still like an open philosophical question. I don't know the answer at all. Of course I don't if it's open. I think that there's more than one way you can understand it. Like you said, you can understand it in terms of geometric phase, but it's still, I don't know, it doesn't quite sit right with me. So I'll give what the sort of Madelung, even the Bohmian interpretation of what this is. I won't get too into it because I don't have enough time and I want to cover the last topic in this course, in this lecture. But, okay, so there is like a third, actually before I do that, let's say there's a third thing which some people say, which is that really it's like we're considering this quantity to be like the fundamental quantity which causes the phase shift. So like say, because this is gauge invariant and it's only dependent on A, so that's the thing that causes the phase shift. But to me that's kind of weird because I'm like, I don't know what that is, and it still seems to act non-locally. So we can kind of clarify what happens in this interpretation by considering the Lorentz force law. So if you remember what the Lorentz force law looked like before, it was m times dv dt, where this thing is like the convective derivative like we had before. So I'm just shortening it, is equal to what we derived as the Lorentz force law minus the gradient of the quantum potential now. We'll assume that the external potential is 0, and you have, but now we're going to consider the quantum potential. So, even though the mechanical momentum depends on, or so this thing, so we know that mv depends on A, right? And that depends on it in both a gauge dependent and a gauge, it depends on it in a gauge independent way. So even if this is 0, so say that this is 0, because we're saying it is 0 in this case, there's no field. The quantum potential, so if equals 0, then Q is still modified by A. And the reason why is because, right, this thing says that this quantity gives you Q, and then this is going to be modified by A. Right? So if Q is still modified by A, then it will be modified, but it will be modified in a gauge invariant manner. So if I sort of write sort of Q in one gauge, and I write it in another gauge, let's say that we have some gauge transformed Q, which is equal to Q that's sort of ungauge transformed plus some function. Sorry, this is maybe getting a little abstract. I'm saying that like this is a quantity which is independent of the flux. When we add flux, right? So this is not, I guess when we add flux is not a gauge transformation. It's a not a gauge transformation. It's a physical transformation. Somehow this thing captures the gauge invariant part of the vector potential, which is not captured in the field strengths. So this is like kind of like this thing. It's kind of like this thing, but you could actually sort of calculate what this should be. And because Q is modified when you add flux, and Q exists in this situation, right? So here I said that Q is 0. Often Q will not be 0. I just did that for the simplest case. Q will not be 0. So it's this thing which exists in the space of the wave function, because Q is really in everywhere where the wave function is defined. It's this thing which acts as like the local causal agent which causes the phase shift. I think this is the most satisfying way that I've understood it, where it's like it's actually the quantum potential which is modified by the flux, and then the quantum potential is the medium by which the flux influences the wave function. and it influences it in some way that will be, this thing this thing importantly is going to be gauge invariant, because of course Q is clearly gauge invariant because Q is dependent on the magnitude, which doesn't vary with gauge. It's still a little bit annoying because unlike, B, which is the nicest thing, you can't measure this either. I mean, Q is this sort of highly non-trivial, weird thing, but at least it gives you a local causal gauge invariant agent. Okay, so yeah, I guess we've already hit the hour-and-a-half mark. I do have one more topic that I want to talk about, but I'll take questions now, and again, if people want to, yeah, I'll take questions now, but I do probably have to move on because I want to talk about that. Is there any thoughts about this? Because I know that it's...
Well, but your argument, you didn't use Q,
Right.
and now you're invoking Q as the agent.
Yeah. So it's...
Yeah, I'm confused.
Like, I'm saying it's doing it like indirectly. I'm saying that this equation says that changing A changes Q, right? And somehow Q changes the velocity field. And somehow, and it's like indirectly causing this thing to happen. I think that I did characterize this. I think I did characterize this correctly, but it is, I kind of did realize as I was saying this, it feels weird because I'm saying that Q is 0, or like I'm ignoring Q. I don't know. This is, I'm sorry to say that I'm probably not 100% actually like ready to answer or prepared to answer that like right now. I kind of realized this like yesterday. I don't know. I think maybe next week I can talk about it in a more satisfying way. But yeah, I'm sorry, I kind of did realize that. There is a way to resolve it though, and I don't have that in my head right now. Yeah. I don't know. So I decided to do this kind of tangent talking about the Aharonov effect because it's very confusing and I spent probably too much time thinking about it. And clearly I still don't have like the correct understanding or the best understanding of it, but at least it's something that is true and it was experimentally verified in like, I think 1960 and then like 100% no questions asked experimentally verified in 1986. So this is like a legitimately, it's a real thing. You can measure like a phase shift in interference patterns when you add flux through a solenoid. Okay, the last thing that I want to talk about, which is almost, let me erase this, which is kind of piggybacking off of this. Is the magnetic monopole. So I don't know, this is like 5, I think. So the magnetic monopole is something that you guys know doesn't exist in nature, pretty much. Like we know that this isn't a thing that's real, but you can. There's a way that you can kind of theoretically construct one in a way that you can construct one in a way that would be completely indistinguishable from a real magnetic monopole. So the idea is to say that if you take a dipole, which is the same idea as a solenoid. So if I imagine a solenoid, and I have a B field flooding going through it, you sort of see that it has this essentially dipolar field, which looks something like that. But if you imagine just extending this thing and making it semi-infinite, so I send this thing out to infinity, then it will look something like this, where now what I've done is I've taken a dipole, I've sent the other pole out to infinity, and so you're just left with one charge, or a charge, at some point, and it's going to look exactly like a monopole. The field would look exactly like a monopole, right? So this is kind of cheating because it's like, okay, well, I'm making this semi-infinite thing, but there's an argument made by like Dirac in 1931 that we will slightly modify here to discuss what happens when you actually want to consider this in the context of quantum mechanics, and is it possible within this sort of newly coupled to quantum mechanics theory to make a monopole. Okay, so yeah, for the sake of time, let me just consider how would we detect that this thing is actually an infinite solenoid. So suppose it's like a delta function, say it's like it's an infinitely thin solenoid. How would we experimentally like actually tell that this thing isn't a real monopole, it's actually this infinite solenoid thing, right? The only way that you can tell if it's infinitely thin, right? The only way that you're gonna be able to tell is by basically by measuring some phase shift around the solenoid. Like you'd see that, like, oh, this thing, you know, it's like a cut. Like it has to. You would somehow actually detect that the solenoid is there. Let's say. If you look at what the B field for this thing should be, because it's a monopole, right? Say that the B field looks the same as what you'd expect a monopole to be. So let's say it has magnetic charge G, and it would just be G over R squared R hat. But that's just what a monopole looks like. And similarly, you would have something that looks like Gauss's law, which is the integral of the B field through some sphere or some surface should be equal to 4 pi times that magnetic charge. Or this is now, I think, basically what Gaussian units are. I mean, you could have some 4 pi is the equivalent of 1 over epsilon naught in our units. Now, if we wanted to detect that the solenoid was really there, we could try to use almost this Aharonov Bohm phase, where, do I want to do that? Yeah, let's say I could sort of consider this Aharonov Bohm phase by considering a path around the solenoid, basically taking a charge, looping it around, and seeing if there's like a phase difference. And you could do this through some interference again. And if you did that, well, you know, right, that the circulation of the charge enclosing this should be 2 pi n, which is equal to, which was the thing that we wrote before, which is 1 over h bar times the integral of the mechanical momentum plus q phi over h bar. So is that, do people follow, I think? Cool, okay. So you can say that that's the circulation, and you can say, well, what is the flux enclosed, right, by this thing? Right, so if we were to measure, if you wanted this to be completely indetectable via this experiment where you're like sort of sending an electron around, or some charged particle around, then you would need this overall phase shift that it sort of sees to be an integer multiple of 2 pi. I guess that's what I should say. What is the flux enclosed in this case then, if this is what we expect? Well, the thing is that because you have this infinite solenoid, you actually have 2 choices, or you have multiple choices for the sort of enclosing surface. So you can imagine a surface that looks like that, or you can imagine a surface that looks like that, right? So the thing is that the net flux, right, should be an integer multiple of 4 pi. Let's see. Yeah. The net flux needs to be an integer multiple of 4 pi of 4 pi g, what am I saying? No, the net flux is 4 pi g times, which is whatever this charge is. But the thing is that phi enclosed, if you sort of go through this thing, you're going to get a net, say that this has flux just phi naught. You're going to get plus phi naught if you sort of enclose this versus this one. So what we need is basically to find the net flux through this surface, we require that, call this surface S1 and this one S2. We need the flux through S1, let's see, minus the flux through S2 to be let's see, oh no, sorry, the flux through this one to be 4 pi g, but then, what is the argument here?
Can't you just use your equation
There is, yeah.
on the top of the, I mean, this delta theta is when you, is Q phi over H bar?
Yeah, no,
Yeah.
I'm thinking,
And if you just take a very small loop around the infinitely thin solenoid, it just picks up the flux through the
yeah,
solenoid.
let's do that. That's good. What am I?
So you need
No,
phi.
maybe I should just do it. Sorry, let me do that. Yeah. Okay. I'll do this in just a second. Sorry. Okay. So yeah, I guess Matthew's saying to do, like, if you consider a if you were to instead consider like a small loop, I guess, you could say that the flux through that is going to be like the phase difference across over the loop would be Q times the phi naught over H bar. And what we want, or I guess, sorry, maybe phi naught's a bad word because this isn't the flux quantum. Then you can say that this thing, if we want this thing to be an integer multiple of 2 pi n, or an integer multiple of 2 pi, then what we can say is that Q times phi, which is going to be just the flux enclosed in the solenoid, is just, as we know from Gauss's law, 4 pi g over h bar is equal to 2 pi n. And so what we find is that the smallest possible charge that this could be is the electron's charge, right? Because we know that electrons exist, so we call that E. And we find that the magnetic charge is actually quantized by the magnetic charge, by the electron's charge, via this equation. But the thing that I was doing before was that it's a little, what if I wanted to do a loop that's bigger? But yeah, well, I don't know, maybe I can stick that next lecture because we will cover a similar discussion. The point is that if you want magnetic charges to exist in a quantum theory coupled to electromagnetism, you actually require, right, for this to happen, you require that the magnetic charge is quantized by the electric charge. And so you could argue that if you had discovered a fundamental charge, which you could use for this experiment, really, not like quarks, which you can't really see in isolation, which you could do this experiment with, which was not an integer multiple of the electron's charge, or it was maybe say less than the electron's charge, then you couldn't actually have magnetic monopoles because this quantization doesn't really work anymore because you would have two fundamental charges, right? Two sort of things that it has to satisfy and it can't satisfy both of them. So you could say, in some way, the fact that we only see integer multiples of the electron's charge is somehow evidence that maybe there is a magnetic monopole. And this is kind of, it seems like esoteric, And it's like, why am I talking about this? It seems almost irrelevant to what we were talking about. Because even though this is a quantum effect, it's like, well, we don't see these, so why do we care? The thing is that you do see magnetic monopoles in other contexts that will be discussed next lecture. Okay, that's everything.
So the condition
Yeah.
is that this infinitely thin solenoid is, you're blind to that if you
Yeah.
try to do an interference around that, and that gives you this quantization, I guess.
Right, yeah, so if you wanted to, okay, let's say, yeah, if the point that I'm making is that this solenoid, if that's the case, is indistinguishable from a magnetic monopole.
Yeah, good.
Yeah, that's the statement that I'm saying. And so then you can sort of follow the remaining arguments. Okay, yeah, that's everything. I guess I didn't go over time, so that's good.
And that's called the Dirac string? Is that
Yeah, this is the Dirac string. I think I got a little bit too caught up in talking about Aharonov Bohm stuff to really get into this, but luckily we do have to talk about it again, probably next week at the end. So, yeah, thanks for coming. Sorry, I know this one is a bit more sporadic than normal, but if you followed it, great. If you didn't, we'll maybe can do even a little bit of review next week. That was already the plan. So yeah, thanks for coming. If you have anything to talk about, I'm happy to for the next 3 minutes or something.
Does the word Dirac string have any connotation to string theory or no?
It's like you can think about this. If this is a delta function, right?
Yeah.
You imagine that like A is singular along a string. It's like literally like a string that you'd be wrapping around. So
I see.
like
Yeah. It's just like really thin.
yeah.
It's really thin and you cannot observe it. Well, if the monopole is quantized, the monopole charge is quantized, then such a UG is H bar 2, then it's not observable by doing interference experiment around that solenoid. If the solenoid is observable, then it's not an isolated particle. It's not
Yeah.
Right, because then it would imply that you have
you have something physical along this string. You want to make sure there's nothing physically, that's observable physically.
Yeah, because we want to treat it like a particle, right? Like,
Yeah, you want to keep
yeah.
the endpoint as a particle.
Yeah.
Yeah, exactly.
Yeah.
That's right.
yeah.
You're saying it shows up like other like what?
We will
what
give
it's
it
called?
a very distinct example next
Okay.
lecture. It will be
Yeah.
it's literally for a magnetic dipole. You have a magnetic monopole parameter space. So you'll see.
Yeah, this parameter space stuff is like something I'm really looking forward to.
Yeah,
Like,
we'll do some.
Yeah.
That's most of the next lecture. So.
Cool. Yeah, no, thank you. I gotta rush to my next section.
I
but-
understand. This one longest. But
Yeah, definitely. I'll stick around.
Make
for
sure
the
you
next
run
one.
your camera or your phone.
yeah.
Yeah, it's challenging.